In this video, we're going to practice drawing resonance contributing structures. So this question is asking to write the major contributing structure for each of the following. All right, so we're just focusing on writing the major contributing structure. Before we start with the first part of the question, let's go over the rules for determining which resonance forms are more important. So there are three rules that help us determine major versus minor contributing structures. The first one, structures with the greater number of covalent bonds contribute more. Okay, so we want the maximum number of covalent bonds. We want to maximize the number of covalent bonds. And generally speaking, full octets are always preferred. The second rule, structures with smallest separation of oppositely charged atoms contribute more. All right, so we want to minimize the charges as much as possible. And then number three, if you do have a negative charge in the molecule, then place it on the most electronegative atom, because electronegative atoms can handle, negative charges better. Generally speaking, we want to put the charge on the atom that can stabilize it best. All right, let's start with the first structure. And when we draw contributing structures, we're going to show the curved arrows as well as the formal charges. And arrows do help us in writing resonance structures, and it helps us, to avoid mistakes. Okay, now we know when we write contributing structures that we can move lone pairs of electrons and pi electrons. These are the only electrons that we can shift or move around. Lone pairs and pi electrons. All right, so looking at the structure here, you have a lone pair of electron on the carbon, and you have two lone pairs of electrons on the oxygen, and then you have this pi bond right here, which is a pair of electrons. So where do we start? So there's not a specific rule that applies to every molecule, but generally speaking, when you have a carbon atom with a negative charge and a lone pair of electrons, that carbon atom is not a happy one, right? So it doesn't like that formal charge. So we're going to start with the lone pair of electrons on the carbon, see if we can shift them somewhere to, eliminate that charge on the carbon. So I'm going to start with the lone pair of electrons on the carbon, and I'm going to move those to form a bond between this carbon and that carbon. And immediately after I do this, I have to shift the pi electrons onto the oxygen. All right, why do I have to immediately shift those electrons? Here's why, because once you shift those or move those the lone pair of electrons to form a bond, this carbon right here is going to exceed the octet. And you know what? Thou shall never exceed the octet. So by doing this, we must immediately shift the pi electrons onto the oxygen atom. All right, let's draw the resulting structure. I'm going to use the double head arrow that we use to represent contributing structures. So here's our CH2. Now it has a double bond with the carbon here. Okay. And now there is a single bond between the carbon and the oxygen, and there are three lone pairs of electrons on the oxygen atom, and now the oxygen atom has a formal negative charge, and the hydrogen is still there, of course. All right, so by doing this, we have moved the negative charge from the carbon into the oxygen. So we effectively drew a major contributing structure because the oxygen is more electronegative than the carbon, and one of the rules is that when you have a negative charge, it's best to put it on the more electronegative atom, and in this case, oxygen atom is the most electronegative atom in the molecule. Now notice an important thing here is that the original structure that I drew had one negative charge, and then the contributing structure that we drew has also one negative charge. Notice that the positions of the atom in both of these molecules are identical. We haven't changed any of the positions of the atoms or any of the connectivities. And most importantly, all the number of lone pairs of electrons and pi electrons is also the same. So these are general rules that I'd like to always go over to confirm that we have the correct contributing structure. So this is our major contributing structure. Let's do part B of the question. Here we have a ring with, again, a carbon atom. There's a carbon atom right here, right, that has a lone pair of electrons with a negative charge. And then you have a nitrogen atom with a formal positive charge. So once again, because you have a carbon atom with a negative charge and a lone pair of electrons, that's quite unstable. So we're going to start with the lone pair of electrons on the carbon, and I want to shift those somewhere to have a more stable structure. Right, so I'm going to take these electrons and I'm going to shift them to form a bond between this carbon here and that carbon. And once again, as soon as I do this, I have to shift those pi electrons onto the nitrogen. And I do this because once we move those electrons to form a bond here, this carbon now is going to exceed the octet. So we must get rid of that pair of electrons. So we push those into the nitrogen. Okay, let's draw the resulting structure after we delocalize the electrons or move the electrons as such. Now we have a double bond between the two carbon atoms, and now there's a single bond between the carbon and the nitrogen, and then the nitrogen has a lone pair of electrons. Okay, what we've done right here is that we have delocalized the electrons, right? We moved the electrons around and we created a contributing resonance structures that has no charges, that has no formal charges. So by doing this, we minimize the charges. So this is a major contributing structure because it has the minimum number of formal charges. All right, let's do one more example, which is slightly different. In this example, you see we have two lone pairs of electrons, a lone pair on the oxygen and a lone pair on the nitrogen, and we have the pi electrons. And we're trying to draw a major contributing structure. All right, so I'm going to draw all possible contributing structures that we can have, and then we'll see which one is the major contributing structure. All right, so I'm going to start by moving the pi electrons into the oxygen atom. All right, and then we'll see what we have. Once you move the pi electrons into the oxygen atom now will have two lone pairs of electrons and no charges. But then the carbon here will have a formal positive charge, right? And then the nitrogen is the same. So by shifting the pi electrons into the oxygen, what I have basically done is I move the positive charge from the oxygen into the carbon. Is that a better contributing structure? Is that a major contributing structure? What do you think? Thinking about the rules that we've just gone through? No. What I did here is that I have less covalent bonds. The number of covalent bonds is actually lower than the structure that I started with. So, and we also have a positive charge on the carbon, which is, again, makes that carbon quite unhappy. So let's see if we can draw another, or we can have another possible contributing structure that would be major. So what else can we do? Well, we can move the lone pair of electrons from the nitrogen atom to form a bond between the nitrogen and the carbon. And let's see the resonance structure that forms when we do that. Now we have a double bond between the nitrogen and the carbon, and you have a positive charge on the nitrogen. So what I've done here is that I moved the lone pair of electrons to form a double bond. So I formed another covalent bond. So I increased the number of covalent bonds by doing this, and I moved the formal charge into the nitrogen atom. So comparing this here to the original structure that we started with, we find that this is a major contributing structure because the positive charge reside on the nitrogen atom and not on the oxygen atom. So remember, when we have a charge, we want to have it on an atom that can stabilize it. The reason why this is not a minor or a major structure is because not only that it doesn't have the greatest number of covalent bonds, but the atoms do not have an octet. The carbon atom here, to be exact, doesn't have an octet, something that is not preferred at all. Comparing the bottom structure to the top structure, we have a major contributing structure. Remember that nitrogen can handle the positive charge better than the oxygen. Oxygen being more electronegative, it's kind of too much on her to take on a positive charge, but the nitrogen can certainly do that. All right, there's a couple more examples in the original question, so do those, do this example, and there's I believe there's a couple more in the question that you have on Blackboard. So do those, and we discuss them in class next time.